Good morning, everyone. Let's pick back up here in Chapter 8. So we're going to start off by trying to talk about bond polarities, where bonds, if we recall, are polar when atoms differ in electronegativity. So hydrogen and fluorine for a molecular compound is about as big of a difference of electronegativity as you can get. So we're going to have, certainly a polar bond, meaning we're going to have a charge separation between the H and the F. Hydrogen's less electronegative, fluorine's more electronegative. Fluorine is electronegative probably because of its small size, high effective charge. That's going to pull electrons more closely towards itself. So the idea of HF is, if we're thinking about formal charge, our formal charge was 0, meaning if we break this bonding pair in half, the formal charge of fluorine's neutral. But if we can have this bonding pair of electrons more shaded towards fluorine, then fluorine's going to pick up that partial negative charge, and then hydrogen going partial positive. And then the idea would be, if we went full plus minus, like the best we could probably ever come up with here would be F minus 1, H plus 1, that would be an ionic compound. We could probably imagine trying to calculate the charge of the atoms. And if it were full plus 1 for H, minus 1 for F, then we would expect the charges to be at best plus 1 and minus 1, and that's plus 1 electron, minus 1 electron. And if you recall the charge of 1 electron, that's 1.602 times 10 to the minus 19 coulombs. So we're going to see that we're going to calculate some charges here because it sort of like proves an idea of what the actual partial charges are. If we look at what a dipole moment is, a dipole moment is a measure of charge separation. So it's a measure of what the charges are and what the distance is, what the bond length is that they're being separated by. So Q is the charges. And so the magnitudes of these charges would be equal to Q. So whatever that partial negative, partial positive, the magnitudes of those charges would be equal to the Q. And then R is the bond length. And so it's on the next slide that we'll actually ask the question, but we can take the bond lengths and we can take the dipole moments and use those to try to convert into what the charges are, what the Q is for the atoms in that molecule. And one of the things you can see if we compare to HCl to HBr to HI is that the dipole moment is decreasing as we go from top to bottom. So as we go to HCl, our dipole moment's decreasing. As our dipole moment's decreasing, presumably what that means is the charge separation's decreasing because our atoms aren't as electronegative. The difference of electronegativity is not as great. So we have a 1.9 difference of electronegativity for HF because fluorine's the most electronegative. Hydrogen's not very electronegative at all. And then if we go to chlorine, not as electronegative, so the difference isn't as great, and that plays a role in lowering that dipole moment. And then you can think lower dipole moment, we're not going to have as developed charges. We're not going to have as big plus and minus charges on the H and the Cl. What this is showing us, when we have a big electronegativity difference, it should be giving us the highest possible charges on those atoms. And then when we start, in chapter 11, thinking about liquids, if you've seen and heard about hydrogen bonds in previous courses, you might remember that when you have fluorine, oxygen, or nitrogen bonded to hydrogen, adjacent molecules obtain an especially strong attractive force we call an H bond. Like two water molecules have a really strong attraction for each other. And it's really the ionic attraction force, the idea that when you have a charge that's relatively small and the charge is relatively high, then that gives you a strong attractive force. So we're going to see that the fact that things like water, things like HF have these high charges allow adjacent molecules in a sample of hydrogen fluoride or water to experience those attractive forces and really allow something like water to exist as a liquid at room temperature, where without that force of attraction it wouldn't have been able to exist as a liquid. And so our dipole moment is this symbol mu here. So mu is the dipole moment is equal to Q times R. Now I'm just going to mention one conversion factor here, we'll see it on the next slide, is that we often measure dipole moments in the unit of debye, named for Peter Debye, and this is equal to 3.34 times 10 to the minus 30, and then coulombs times meters. make sure this is clear here, times 10 to the minus 30. And this is always a given. If you need to do a problem, we'll give you the conversion factor between the non-SI unit for charge separation for the dipole moment and this unit of Debye as being related to the Coulomb and the meters. But I just want us to see now that if you had a plus and a minus 1, like if it was plus 1H, minus 1 for F for an ionic compound, then our charge would be plus 1.6 times 10 to the minus 19 coulombs for H and minus 1.6 times 10 to the minus 19 for F. So that when we get a charge out on the next slide, we're going to get a charge kind of in coulombs, and we can start thinking in terms of charge relative to an electron, what's the charge? Because what we're going to really want to see is that the charge is somewhere between 0 and minus 1 for F, and between 0 and plus 1 for H. Okay, so let's look at this problem here. So the problem's asking us or telling us that the bond length and dipole moment of HF are what they were in the previous slide, 0.92 angstrom. And of course, we're probably remembering this would be 0.92 times 10 to the minus 10 meters, because 1 angstrom is a 10 to the minus 10 meter. And then the dipole moment is 1.82 Debye. Can we calculate the charges on fluorine in a molecule of hydrogen fluoride? And then, you can imagine at the same time we could calculate the charges on H, because the H charge is going to be the positive charge, and fluorine should be negatively charged. Because again, fluorine's more electronegative, pulls the bonding pair electrons closer towards itself, develops that partial negative charge. And so if we're examining the choices, the only possible answers would be the negative values here. So the only possible answers would be B, D, and F. We would already be able to roll out that the charge on fluorine cannot be positive for this molecule. And so here we're given the charge of an electron. So if you see this on a test, we'll give you the charge of 1 electron. We'll give you this conversion factor for Debye into Coulomb meters. And so then if we want to solve for this, we're using this equation that the dipole moment is equal to the charge times the bond length. So we can solve for the charge. But we just have to account for units. That's the only tricky part of this problem, is that we just have to do some unit conversions to get the charges out in a unit that we can understand. If I just take 1.82 Debye and divide it by the 0.92 angstrom, you can kind of see, or it would be hard to tell what the unit would be for charge. And so this is why we just have to go through the process of converting 1 Debye into Coulomb meters. And then we've already converted it on the side, but we can convert angstrom, 1 angstrom, 10 to the minus 10 meters. And so then the angstrom cancels, the meter cancels, the Debye unit cancels, and we're left with the charge and a unit of charge of coulombs. And now let's go ahead and leave it in coulombs to calculate it, see what it is, and then we can try to convert it to the charge relative to an electron. So let's just calculate this in coulombs. So 1.82 times 3.34 E minus 30 divided by 0.92 E minus 10. I get 6.61 times 10 to the minus 20. And the unit's coulombs. And this is definitely less than 1.6 times 10 to the minus 19 coulombs, right? The charge of 1 electron. So we're definitely on the order of magnitude of a partial charge. And the way we can calculate the charge relative to that of an electron would be just to use the charge of the electron, just to use that 1 electron's charge is 1.602 times 10 to the minus 19 coulombs. So if I just divide this by the charge of the electron, I get 0.41. And so coming back to our Lewis structure picture, our negative charge, F would be negative 0.41 units of charge relative to an electron, we just call it electron charge units. And then hydrogen would be plus 0.41 electron charge units. So answer B there would be the answer. But now what we're getting a glimpse of is, one, just how to do this calculation, but then two, just seeing how partial negative the charges are here for one of the most polar compounds, one of the most polar covalent compounds that we can have. Now, like lithium fluoride would be like a full plus on lithium, F full minus. Here, H almost about half for H, and then negative half for F. So we're almost exactly halfway between nonpolar covalent and ionic. So one thing that sometimes we talk about is we would call this like 41% ionized. Just to think that if you had the full -1 charge, that would be 100% ionized. So you can think of fluorine here as about being 41% ionized is another way of thinking this too. And so then for like HCl, we could run through the calculations for HCl, but we would see, I think for HCl, the charges are like 0.27, so minus 0.27 and plus 0.27. HBr even lower, HI even lower. So as our electronegativity difference is decreasing, then our magnitudes of charge are decreasing at the same time. Okay, so what we're seeing here through this calculation is just what we mean by partial charges. So partial charges probably not quite greater than half a unit of negative charge and positive charge being distributed across a molecule. If we then start thinking of something like water, the way this ends up kind of working, we're picturing a Lewis structure for water where we have, we kind of had this Lewis structure last time. We're talking formal charge. Like a formal charge picture says assume the bonds are equally shared and then calculate kind of the charge you would have for the atoms inside this box. For oxygen, the charge would be 0. The hydrogen, the charge would be 0. So the formal charges are 0. But then think about the actual charges. Then think about electronegativity. So once you think formal charges, so we're going to sketch Lewis structures a lot in this chapter. We're going to then look at the Lewis structures, try to assign formal charges. Formal charges are just assuming nonpolar covalent bonding. What are the charges the atoms would bear? And then think about what's going to happen once we then think about the relative differences of electronegativity. O's more electronegative than H, so oxygen is going to be pulling those bonding pair electrons closer in towards itself. So oxygen is really going to have a partial negative, like actual charge. So the formal charge is 0, but the actual charge of oxygen and water would be negative. And then we'd end up with some partial positives on hydrogen, where they're obtaining the positive charge because they're less electronegative. So as we get into Lewis structures, think that Lewis structure is a model. It's going to try to model where the electrons are in a molecule if we're assuming nonpolar covalent bonding. And then once we release that constraint and start thinking, okay, bonds can be polarized, let's start thinking about which atoms are more or less polar, so we can think about the more electronegative atoms pulling electrons more closely towards themselves. Now, let's go back real quick to oxidation numbers. So we probably remember those from chapter 4. If we were assigning the oxidation numbers in water, our usual rule for hydrogen's +1 in molecular compounds, oxygen's usually -2. And so the idea of oxidation numbers is they're getting the magnitude of this charge here. You know, they're trying to get the sign of the charge in the proper sign, so that hydrogen should be the positively charged atom. We see it's partial positive, and oxygen's partial negative. But you can see this really isn't, of course, an ionic compound. This isn't H+, O2-, like we'd expect for like calcium chloride. And calcium chloride, a little bit different. We really have, you know, these charges developing here and have an ionic compound form. So just making sure we see the difference between something ionic that really has the charges that we expect from oxidation numbers and from the charges we know that those ions have from like nomenclature. And then water, we assign the charges, but they're just really so that we get the signs right on these partial charges. Okay, so again, for formal charge, we're assuming the bonds are 100% covalent or 100% nonpolar. And so for diatomic molecules, we're going to try to satisfy the octet rule if it's possible. This really is an important distinction for CO. We'll see that as we get to bigger molecules, we don't necessarily have like an octet rule has to be satisfied rule as part of our Lewis structure rules. But for diatomic molecules, we really want to satisfy the octet rule. So when I look at CO, I have 4 plus 6 electrons, 4 for carbon plus 6. One thing that we're going to probably get in the habit of is for a Lewis structure, we're probably going to want to track the valence electron count so that we can know how many electrons we have to distribute around the molecule. And then if I have 10 total electrons and each atom needs an octet, then I think you can probably see that the only possible Lewis structure would have a triple bond. Because if I tried to use a double bond here, I wouldn't have enough electrons to give each atom 8 electrons. Like this would take 12 electrons, and I don't have 12 electrons. Single bond would be even worse. We'd need 14 electrons. So if I have 10 electrons on a diatomic molecule, then I'm going to need a triple bond to satisfy the octets of both atoms. So by satisfying the octet, I mean just picture 8 electrons in total, counting all the bonding pair electrons, and then 8 electrons for the other atom. So both atoms are satisfying the octet rule. But then when we think formal charges on the atoms, we then break the bond in half. I wanted to mention that there is an equation. I'm not big on this equation because it's easy to forget or not understand what it means, but the formal charge equation is like the valence count for the atom. Just looking at the atom from the periodic table, like carbon's 4, oxygen's 6, nitrogen's 5. So taking that valence count for the atom, then you subtract all the non-bonding electrons. So if there's non-bonding electrons, we subtract all of those, and you subtract half of the bonding pair electrons. And so that's just breaking the bonds in half. So if you look at the equation, if you've seen the equation for formal charge in the textbook, if you come across it, the breaking of the bonds in half is why I like to make sure that I just literally break that bond in half, and I'm almost like just drawing a box, because then I'm keeping all the non-bonding atoms on the one atom they reside on, and then I take half of the bonding pair electrons. And so for carbon, if we look at either the box or the rule, I'm taking the count for carbon would be 4, is its valence count that it should have, has 2 non-bonding electrons, and half the bonding pair electrons is 3. And so that's going to give me a formal charge of -1. So carbon ends up with a formal charge of -1. And then oxygen should have 6. And it has the 2 non-bonding pairs, the 2 non-bonding pairs, and then the 3 from the bonding pairs. So we have 6 bonding pairs. Half of them is 3. So 6 minus 2 minus 3 is +1. The formal charges of the atoms, if we add them up, just like oxidation numbers, should give us the charge of the molecule. So -1 plus 1 equals 0. Carbon monoxide is uncharged. So we can see carbon monoxide's Lewis structure is going to be best described. If I'm writing a Lewis structure, I'm probably just going to write it like this. C, triple bond O, lone pairs, and then -1 for carbon, +1 for oxygen. So those being its formal charges. And so that's kind of the way Lewis structures are going to go. We're usually not going to indicate 0 charges unless we're just making sure to drive home the message that the formal charge is 0. So a Lewis structure usually should show the formal charges of any atom that's not 0, and then where the non-bonding pairs of electrons are, where the bonding pairs of electrons are, and it should demonstrate all the valence electrons being distributed, 10 for CO. Now, does anything notice anything weird about CO? Is there anything that strikes you as being like surprising? Like oxygen's more electronegative and it's positive. And that is kind of peculiar. But now think about what happens once we calculate formal charges, then think about what the atoms are going to do. Oxygen's smaller, has a higher effective charge. It's going to be pulling these bonding pair electrons more closely towards itself. So it's going to pull those bonding pair electrons more closely towards itself. It's a fun problem, but it just becomes another problem just like the HF problem we did. But if I gave you the dipole moment of CO, and if I give you its bond length, you could calculate the charges. The charge on O ends up only being about plus 0.02 electron charge units once all said and done. Once you imagine the electronegativity playing its role, that charge drops almost to 0, but still positive for oxygen. And then the carbon's charge goes to minus 0.02 electron charge units. So these are the actual charges in CO from the, this is from a mu is equal to Q times R problem. And I think it's on one of the practice quizzes actually has this specific problem of going through CO and calculating these charges. But it does still turn out that O is positively charged, and then carbon's negatively charged. In fact, carbon monoxide is so poisonous to breathe in because it's actually the carbon that, so when you breathe, right, oxygen binds to hemoglobin. I think we know this. And so when you breathe CO, the CO binds to hemoglobin. Well, O2 binding to hemoglobin is good because it's transported and then it's removed and then comes back, and then you can it's replaced with CO2, and then you exhale, the CO2 goes out, and then the O2 can be rebinded. So there's this like rebinding of O2, rebinding of CO2 that can happen with hemoglobin and myoglobin. Well, once carbon monoxide binds to hemoglobin, that carbon stays stuck. It never comes back off. So the only chance you have if you become poisoned by carbon monoxide is that it's not so much that it binds to all your hemoglobin, and then also that you have enough time to make new hemoglobin. So over time, your body will kill off the hemoglobin to make new cells and replace those. That's your chance of survival if you do end up with carbon monoxide poisoning. So very dangerous because this irreversibly binds through the carbon. Just another kind of point of that the carbon really does bear that negative charge in this molecule despite being the less electronegative atom. So long-winded approach, but for diatomic molecules, we get to the best Lewis structure satisfying the octet rule, and then we can still think about relative differences of electronegativity and how the bonding pair electrons are going to slant more towards O, but it's still not enough to take O back to negative. So oxygen remains positive in carbon monoxide. Then for cations and anions, when we're doing our valence count, we just look at nitrogen. Nitrogen should have 5 valence electrons. Oxygen should have 6. A positive charge kicks one of those electrons out. So we have to lose a valence shell electron to obtain that net positive charge. So an NO molecule with 0 charge, we can, I think this comes up later, but if we had a nitrogen and an oxygen bonded together with no charge, then that would have 11 electrons. But with a positive charge, we've removed 1 down to 10 electrons. So really simple Lewis structure. This will just be nitrogen, triple bond to oxygen, just like CO. And then this one's also strange because nitrogen's formal charge ends up being 0, 5 minus 5. And then oxygen's formal charge ends up being 6 minus 1, 2, 3, 4, 5 for plus 1. And so do you expect the charge on NO to be fully plus 1? Probably not. The actual charge is probably going to be reduced due to the electronegativity of the bond, but still we would probably expect oxygen to be the positively charged atom in a molecule of NO+. And then lastly, for NO-, we'll revisit NO without the electron later. But for NO-, just remember for anions, we're adding those electrons into the valence shell, so we have 12 electrons. And so this should look like O2, which has 12 electrons, so a double bond. And then we give 12 electrons across. And so for our formal charges here, we can break that bond in half again. Nitrogen should have 5 valence electrons. We have 6. So that's how we come up with -1 formal charge for nitrogen. And then our oxygen is 0. Now oxygen is more electronegative. Again, we're going to expect that the bonding pair should shade towards O. This is a weird compound. This would actually be a neat one to try to figure out what the actual charges are, because we're going to end up pulling some charge back towards O, and we're going to end up probably with an N and O that are fairly similar in charge once electronegativity kind of kicks in. So just know that the idea of electronegativity would be, let's get to a Lewis structure that gets to a point where we can then think of electronegativity playing its role and how it's going to shade those bonding pair electrons towards the more electronegative atoms. Okay, NO with the neutral charge, we'll talk about that later. I want to go through some more examples before we come back to trying to assign electrons for a molecule that has an odd count of electrons. Okay, so for diatomics, we're trying to satisfy the octet rule, and if we can, we're just doing so, and then we're just distributing the formal charges or calculating the formal charges from there. Now, whenever we have a triatomic molecule or larger, we've seen some Lewis structures. Like, it's not necessarily wrong to do like a dot structure. Like when we were looking at oxygen and kind of coming up with this dot diagram and hydrogen, like this is one way to come up with the Lewis structure. But what we're going to find is if I give you a molecule like SO4 2- or ICl4-, if I give you some really peculiar molecules, you're probably going to have a hard time starting from a dot diagram and sketching a Lewis structure. So we'd probably like to have a more general way of sketching Lewis structures that kind of works from the ground up. Like we can maybe assign Lewis structures with these rules for all molecules, simple and complex. And so the way our Lewis structure rules are going to work, we're going to sum up our valence count for all the valence electrons in the molecule. We're going to try to identify the central atom. That's not going to be such a hard task. It'll usually just be like when we have like SO4 2-, like the first atom is usually the central atom. Whenever you get the things like H2O, it's them picturing that the things are probably attached to O. So it's just usually trying to figure out are the hydrogens on the O, or are we giving like the central atom first? So that the central atom could be first or last, but it'll be obvious once you get into a lot of examples. Hydrogens can't bridge, so hydrogens are always on the outside, for example. And so then once we figure out the central atom, we're going to attach all of the other atoms that are attached to it with single bonds kind of first and begin there, because that's like the least amount of bond that you can have as a single bond, at least within a Lewis structure. We're going to complete the octets of our non-central atoms. So we're going to try to make the non-central atoms like have a filled octet for whatever type of the atom it is. Like a hydrogen's filled octet is obviously good without any non-pair electrons. But if I had a Lewis structure for like, let's say OF2, there's like a lot of examples that sometimes right now it'll be good to see an example. We might revisit some of these later. But if I'm doing a Lewis structure for a molecule like OF2, do you kind of see how O is going to be the central? The two Fs would have to be attached to it. That's why we would write the formula this way. And so our oxygen's a central atom. Our valence count would be 6 for O, 2 times 7 for F. So our valence count would be 20 valence electrons. And so our rule so far would be attach those non-centrals to the central. I'm not going to be too worried about geometry. I'm not too worried yet about why I'm going to do it 90 versus 180. We're going to talk about geometries in the next chapter. So I'm not going to concern myself too much with worrying about, should I draw this at a 90-degree angle or 180? We'll talk about that in the next chapter. But just look at the rule. It says complete the octets of the non-central atoms first. So that would be the fluorines. I don't automatically put electron pairs in the central atom. Like notice that there's nothing right away that says, and put electrons on the central atom. Like I might be looking at O saying, looks like I have room for 2 electron pairs, but let's hold off. So what we want to then do is, if I don't have enough electrons, so like at this point here, we may wonder how many electrons have we distributed? There's across each of those fluorines, 2, 4, 6, 8, 10, 12, 14, 16. I've distributed 16 electrons. If I had already distributed too many, I'd have to be making like multiple bonds. So if somehow too many electrons have been distributed for what we have to start making double or triple bonds somewhere. But that's not the case for this molecule. I actually have 4 electrons left over that haven't been assigned. And so any unassigned electrons are placed onto the central atom. So like when I have these 4 electrons that haven't been assigned anywhere yet, they go onto the central atom. So that's how we know to place electron pairs onto a central atom, is just by seeing that there's electrons that are left over in the process. So let's contrast that Lewis structure with like BF3 for a minute, and then also try to get through the rest of the rules. But for BF3, boron only has 3 valence electrons, fluorine's 3 times 7, so that's 24 electrons, so we have a central boron. 3 fluorines. I'm going to move this fluorine down just so I have more room to write the electron pairs. Oh. So I'm going to give each fluorine its octet. And what I want to see right away is that we're not going to look at boron and say, oh, it has room for 2 electrons, so I'm going to put 2 electrons on boron. Like, that's not part of the rule. The rule isn't saying, oh, I should put 2 electrons here. That's not the rule. So what we need to do is just fill the non-central atoms' octets first, then count up the electrons that we've used. We've used 8 times 3. We've used 24 electrons. We have none left over. So there's no electrons left over for boron, so boron's just going to have to live without having its octet satisfied. Or we're going to have to maybe think about one other step about if we should consider the octet of boron, but this is, at this point at least, a good Lewis structure. And so if we at some point have used too many electrons, we have to use multiple bonds. And then should we consider multiple bonding? Well, I think we should do so if it's going to lead to minimizing magnitudes of formal charge. So something we might want to do for OF2 and BF3 right now is calculate the formal charges for boron and fluorine and oxygen in those molecules. So do you guys see OF2, that the charge of oxygen, formally, the formal charge would be 0? Is that pretty easy to see at this point, that we're just breaking these bonds in half? And then calculating the charge that O would have with 6 electrons, that's neutral. Fluorine with 7 electrons is neutral. And then boron, the boron should have 3 electrons, and it does. So boron's charge is 0, fluorine's charge is 0 in BF3. So we have neutral formal charges in both molecules of OF2 and BF3. So if I'm going to use a multiple bond, it's actually going to be kind of a silly idea. So if I think about making a double bond, like maybe I'm going to move these electron pairs in here, if I use this Lewis structure, or write this Lewis structure here, and think, okay, what if BF3 does this? Is that something BF3 wants to do in terms, is this something we want to model BF3 doing? Think about what happens when I move this electron pair in here. What happens to boron's formal charge? What's it now? Well, it should have been 3. I now pack 4 electrons around boron. This makes boron -1, and it makes this fluorine here that we made the double bond with it, makes it +1. Think about that for a minute. Fluorine wants electron pairs. Do you think it's going to give an electron pair up for free, for like no reason? And then boron's like, hey, I don't have any charge. And it's like, can you imagine fluorine like, well, do you want some electrons? Well, how am I supposed to pull those in? You know, so it doesn't make much sense that we would go with this Lewis structure. So we're not going to go with that Lewis structure. And the rule with the part of the rule that tells us not to do this is that we're not going to increase the magnitudes of formal charge. So we're going to consider multiple bonding if doing so minimizes magnitudes of formal charge, not maximizing the formal charge. So the octet rule does not allow for an octet to expand beyond 8 electrons for certain atoms. You know, so like we have to be careful sometimes too that we don't want to expand an octet through this rule too. So we want to be careful when we expand an octet through multiple bonding. We'll talk about that when we get to examples where that might come up. And then the formal charge rule, we can expand octets in the 3rd row and beyond. We'll see some examples of when this can happen in some Lewis structures. So we'll talk about a few molecules that have, you know, like 2 different Lewis structures that will end up being possible and good answers for their best possible Lewis structures when we get to a few more examples. So we'll see some examples of these rules here as we continue, where those rules will make a little bit more sense and we have some different examples. Okay, so I want to circle back to before I move off of OF2. So for OF2 and BF3, the atoms have 0 formal charges all the way around, and that's good. All the atoms happen to be satisfying the octet rule except boron, which is deficient, but it's okay because its charge is neutral. So that's probably a good reason why something BF3 is a stable molecule, is because it has those neutral charges. So let's look at CCl4 and some of these examples here. So let's do this on the next slide, or a blank slide. So CCl4. So carbon's count would be 4. 4 times 7 for the chlorine, so that's 32 electrons. And so for our Lewis structure here, we're going to have the 4 chlorines single bonded, give the chlorines their octet. And then that's our 32 electrons. That's 8 each. And so that's our Lewis structure. The only last part of the Lewis structure you would consider is the formal charges, but there's 0 and 0, so there's no need to consider multiple bonding. All the atoms are satisfying the octet rule. So you can kind of think when you get to a Lewis structure, is the octet rule being satisfied? Do I need to worry about formal charges? Everything's 0, octet's being satisfied, so that's good for CCl4. One of the other molecules was NF3, which is kind of like BF3 in a way, just where nitrogen, though, has 2 more electrons. So we have 5 plus 3 times 7 for 26 electrons. So this is the case where we get to the same type of Lewis structure we had like for BF3, but where we have 2 more electrons. So I've distributed 24, 2 electrons left over, placed onto nitrogen. Now, I think it's probably important to mention that I don't think molecules are placing their electrons in this way. You know, like this is just a way of seeing how we're going to distribute electrons across a molecule. I know what it was I was trying to think about for OF2 and BF3 that I wanted to talk about before we moved off them was the electronegativity. So think about how electronegativity is going to kick in. Chlorine is among the nitrogen, oxygen, fluorine, chlorine, the 4 most electronegative elements. So chlorine's more electronegative than carbon. It's going to be pulling electrons towards itself. Chlorine's going to develop a partial negative charge in this molecule. The true charge of carbon will be partial positive. If we knew the partial negative of the chlorines, carbons would be 4 times that charge. So we're going to see some partial charges in CCl4. We would see partial charges in OF2. Let me sketch the OF2 again real quick, because there was an analogy I wanted to draw. For OF2, remember oxidation rules, fluorine stays negative. So when we looked at like OF2 by oxidation rules from chapter 4, we would have said fluorine stays negative and oxygen goes to +2. Well, which atom do you think is partial negative? Which one's more electronegative? Fluorine's more electronegative, so it's going to be pulling those bonding pair electrons closer towards itself, going partial negative, and oxygen going partial positive. So you can see the oxidation rule was just really foreshadowing electronegativity trends. And so it was just foreshadowing that fluorine's more electronegative, it's going to go negative, oxygen's less electronegative, will go positive. I think was the other one on the previous slide SF4? I think it was. There was a couple Lewis structures the previous slide mentioned. I think SF4 and SF6 were the other two. SF4, this Lewis structure here has 6 for sulfur, 4 times 7 for the fluorines. So that's going to give us 28 plus 6. That's 34 total valence electrons to distribute in our Lewis structure. So central sulfur, 4 fluorines. Again, I'm not worried about geometry. Give the non-centrals their octets. And let's even think about this rule for a minute. So when I calculate, I've used 32 electrons, and I have 2 left over. Do we get the idea that the non-central atoms, their octets are filled? So we've already filled their octets. There's really nowhere to put electrons around a fluorine atom. But now we look at sulfur. There's really no electrons. Is there room on sulfur? Because its octet's being filled too. Well, there's not much of a choice between putting those electron pairs on that central atom. One, because usually the central atom is going to be the bigger atom. When these types of compounds form, notice sulfur is expanding its octet. But the expanded octet can happen in a compound like this for a couple of reasons. One, because sulfur is big. This is going to happen third row and beyond. like we wouldn't see OF4. Like, or at least that wouldn't be a stable compound that you're going to put into a gas cylinder or a chemical container and ship. So with oxygen, if you imagine O instead of F, where oxygen has to expand its octet, it just can't happen like it can for sulfur. And so for the second row, we just don't see molecules that exist commonly that expand octets. But in the third row, we will see this. But now think about how this is going to happen in the real molecule. Like, think about how an atom like sulfur can expand its octet. Well, don't you imagine that the fluorines, being electronegative, are going to be pulling electrons back off the sulfur, making room for those extra electrons. And so you're also not going to have this type of compound form without a really electronegative atom on the periphery of the molecule making room for those extra electrons. And so the Lewis structure expands the octet. So the Lewis structure expands the octet. We have to remember the Lewis structure is a model, and the model is not the molecule. Okay, the molecule is smarter, maybe, or more advanced, or considers things beyond just our basic Lewis structure. What the molecule considers is just electronegativity differences. That if we're pulling charge off sulfur, then sulfur can have electrons lost from it on average, and then therefore make room for those two extra electrons. So it's really not necessarily expanding its octet in reality. It's just the Lewis structure is showing that expanded octet. I do think that the book, like we'll say SF4 has an expanded octet. I think that's slightly wrong vocabulary. I think we should say the Lewis structure we show for SF4 shows an expanded octet. The real molecule is going to find a way through using its only available like 4 orbitals that fit 8 electrons. It's going to find a way to use those 4 orbitals to fit those electrons around it. But that gets a little bit too nuanced maybe for what we're trying to see in chapter 8. So I don't want to worry too much about how an atom expands its octet or if it really does or doesn't. But I think for the real molecules, you can see that these expanded octets are happening with electronegative atoms that pull the electrons back off the central atom. We'll see that also for SF6, which of course has to expand its octet in its Lewis structure. So we have 6 plus 7 times 6 for 48 electrons. And so this molecule here will have 6 fluorines attached. We can maybe think about, this is actually kind of what the molecule looks like. We'll see this is like what we call an octahedral geometry in the next unit. But this is kind of like what SF6 looks like, at least within its Lewis structure. And so that's 6 fluorines, 8 each. So that's all 48 electrons. But you can see sulfur appears to have 12 electrons surrounding it, so sulfur has an expanded octet. Within the Lewis structure. By the way, for SF4, the central sulfur, do you see how it's 6 minus 1, 2, 3, 4, 5, 6 for a neutral charge? So the sulfur is neutral charge, fluorines are neutral, and the same thing here, that the sulfurs are neutral and the fluorines are neutral within their formal charges. Do you really think the fluorines are neutral in SF6? Probably not. You know, so these fluorines are, and certainly not, they're going to be pulling electrons back towards themselves. There's actually a really interesting model for SF4. This isn't something to be too concerned about, but if you imagine a model where we kind of move a bonding pair of electrons onto one of the F's to make a minus. And then in return, we make a positive charge on sulfur to kind of hold the negative plus. Imagine we do that across all 3 of the centers simultaneously. That's a model you can come up with for SF6 to where it actually would have a minimized octet, where it actually have less than an octet. So we can actually imagine like a Lewis structure where we're making like these partial ions, and then these could be in equilibrium or in resonance with the other bond doing this. So imagine we reform that bond here, and then we resonate or change the charge over to here with that minus. And imagine you do that across all 3 bonds kind of simultaneously. So you might actually only have 3 bonds between F and S being distributed, and then the fluorines just adopting like negative charges to kind of hold on to the rest of the charge of the molecule. So in other words, molecules are smart. They're going to find a way to use the orbitals and the space that they have so that they don't necessarily have to worry about expanding their octet. But the Lewis structure does show for SF6 that it would have 12 electrons around sulfur and therefore have what we call an expanded octet. But that's fine, this molecule exists. There's a fun demo, I really hate doing it though, where you can breathe SF6 in and it makes your voice deep, because you can actually feel the fumes coming out because SF6 is so heavy. I've done it once and I just really can't stand doing it. It just seems probably pretty toxic. But it makes your voice deep, kind of the opposite of helium. And so SF6, and it also shows that it's a stable compound that can exist and you can put it into a gas cylinder. So a stable enough compound with the expanded octet in its Lewis structure. Okay, so let's kind of continue looking at more Lewis structure examples, kind of going through some more nuances of the rules. We'll skip the ones that we've already looked at. So NH4+, we looked at it previously last time. We had NH4+ on the chalkboard, if you recall. But in terms of a rule here, just seeing how our rule that we just come up with would work for NH4+ would be, let's get the valence count here. So 8 electrons, 5 plus 4 minus 1. And then nitrogen, single bond the hydrogens. Hydrogens don't need any more electrons to fill their octet. Remember, octet is kind of like a word for nearest noble gas count. So for hydrogen, 2 is good. For our second, third row atoms, we're going to want 8. And so that's good here. And then our nitrogen ends up with the positive charge, 5 minus 4 for the positive charge. And then all the hydrogens being neutral and formal charge. And so that's how we can come up with NH4+ with the rules we just laid out, where we previously had it last time more from like a dot diagram where we came up with it. Let's contrast even BF3. Remember how we got to the 3 fluorines, no charge on boron. Let's look at COCl2. Pretty important molecule. This is phosgene. Like, we're probably picturing that all of these atoms here are on chlorine, or on that central carbon. So I have 2 chlorines and an oxygen. And so then if I follow my Lewis structure rules, I come up with this structure here. And you guys see how that kind of right off the bat looks a lot like BF3, how BF3 looked. Now let's count up our valence electrons. Maybe we should have started there, but 4 for carbon, 6 for O, 2 times 7 for the chlorines. And so that's 24 electrons. And I've distributed 24 electrons. And so let's get into that rule about reducing magnitudes of formal charge. What's the magnitude of formal charge of carbon right now? Carbon should have 4 electrons surrounding it. It only has 3. So right here in this Lewis structure, carbon's charge is positive. And then oxygen should have 6, and it has 7. So that's minus 1. And then the chlorines are 0 and 0. And so we consider multiple bonds for 2 reasons. Either we've used too many electrons, and we need to get rid of some, and we use multiple bonds to bridge between 2 atoms. Or in this case, we can consider a multiple bond if I can move these 2 electrons here, and then that result reduces the magnitudes of formal charge. So think about what that does to the formal charge within this structure here. I now have 4 electrons around that carbon. So I've changed the formal charge to 0. And then I've changed the formal charge of this oxygen here to now be 0 as well, because it's now 6 minus 6. And so do you see how I've reduced the magnitudes of formal charge? So we make multiple bonds, and we reduce the magnitudes of the formal charge in the process. If we left the single bond, minus 1 plus 1, double bond 0, 0. So for BF3, if we make the double bond, it went from 0, 0 to plus 1, minus 1. So that's bad. That's putting charge to where it doesn't want to go. In fact, for BF3, boron was neutral, fluorine's 0. Fluorine's trying to pull electrons off of boron. It's not trying to give boron electrons, it's actually trying to take the 3 that it has away from it. Okay, so COCl2, carbon, oxygen double bond, 2 electron pairs. We're going to see a trend now. Sometimes trends help, but when we're trying to do the Lewis structure rules, we're usually going to apply the rules first, and maybe we can look for trends as a double check later. But we're going to see in a lot of stable compounds, oxygen will form 2 bonds, 2 lone pairs. Either 2 bonds through 2 single bonds, or 2 bonds through a double bond. That's going to be common for O. We're going to see nitrogen tends to form 3 bonds with 1 lone pair. And again, it could be 3 triple bonds, or 1 triple bond and a lone pair, or a double and a single and an electron pair, or 3 single bonds and an electron pair. And then lastly, we're going to see carbon tends to form 4 bonds, no lone pairs. So for water, and again, this is really just making sure we see that, like, we came up with the Lewis structure of water before. Let's make sure it makes sense with the rule that we're working with here. 1 times 2 plus 6 for 8. Oxygen, single bond to hydrogens, that's 4 electrons. 4 left over go on to oxygen. So we can go to a dot diagram for water and get the Lewis structure, or you can apply the rules and get to the Lewis structure. OF2, I think, works with both. We've done that already. So in terms of, should you go to a dot diagram or should you just apply the Lewis structure rules? Usually I'm just going to the Lewis structure rules because I know they work for everything and they're pretty easy to apply. So I go 5 plus 5 times 7, that's 40 electrons. And so I just put 5 fluorines around phosphorus. Again, I'm not going to concern myself too much with geometry here in chapter 8. We'll get to that when we get to it next chapter. But I end up with 5 fluorines with 8 electrons. Now, I sometimes get the question of, can I just write the pairs as a line? I don't care if you write the electron pairs as a line. I prefer to write dots, even though the lines are a little bit more clear. I just really like thinking that the electron pairs are still, they're not like fused together. I don't want to get too confused on what the electron pairs are doing. So I like to show them as dots when I write the structures. And so that's all 40 electrons, none left over. Phosphorus is happy, all neutral formal charges, 5 minus 5 for phosphorus, 7 minus 7 for fluorines. And so no formal charges. Like, we don't need multiple bonds, the formal charges are happy. What about chlorine trifluoride? So 7 plus 7 times 3 is 28 electrons. So central chlorine, 3 fluorines. And then one of the tricky parts of ClF3, and I see the slide, is that we just go like this and call it a day. Because we think, well, that gives chlorine an octet. But you see, we just have to make sure we count the electrons used. We've used 8 times 3. That's 24 electrons used. There's 4 electrons left over. So chlorine ends up with 2 electron pairs around it. It expands its octet in the process. And again, chlorine's in the 3rd row and beyond, so that's okay for chlorine. And we expand its octet, and we go with this Lewis structure here. And again, the fluorines are pulling electrons away from the chlorine, where chlorine's formal charge is, interestingly, notice that it's neutral. Chlorine should have 7 electrons surrounding it. It has 1, 2, 3, 4, 5, 6, 7 electrons surrounding it for 0. So we have 0 formal charges all the way around. And of course, the fluorines are pulling electrons away because they're really electronegative. Let me finish with NO3 minus, because there's one thing that I want to make sure that we see here for NO3 minus when we're doing our Lewis structure. So 5 plus 3 times 6 plus 1 for that negative charge. So that's 24 electrons. So nitrogen, 3 oxygens, lone pairs. And so that uses all 24 electrons, none left over, so no lone pairs for nitrogen. What's the formal charge of nitrogen? Should have 5, only has 3, it's plus 2. So we do this, because that changes it to plus 1. That's good, right? That we reduce the magnitudes of formal charge. Now, what about this? What's bad about that? Why do we not do that? Nitrogen's in the 2nd row. We can't expand the octet of 2nd row atoms. So for the 2nd row, we have to keep the octet filled. So here, the filled octet is good. So we stop at that filled octet. We can't expand the octet of a 2nd row atom. So if you have that in the back of your mind, it's a weird rule. It comes up a few times where second row atoms, we're not expanding octets. When we get to some third row elements and beyond, we can expand octets, but we're not going to expand the octet of something like nitrogen. We remain with a double pair, 2 singles. But we'll pick up with these other examples on the slide and get into something called resonance on Friday. All right, guys, thanks for the attention. Have a great day.